So here is our PWM test circuit with the motor drive. It's a slight modification what's in the handout, but only to show how to measure the speed and the like. So what we have is our motor. Because we're going to drive this motor electronically, we need this diode that protects the transistor down here. I'm using a BJT NPN tip 31B. It's a power transistor. It can handle several amps. I'm going to use 15 volts as my motor supply. I'm going to read the speed through this optical encoder, which is mounted on the back of the motor. We're going to use a PWM signal to drive the transistor. We have a 1K ohm resistor for the base drive just to protect the base. The frequency is going to be varied from 1 to 20 kilohertz. To see what kind of performance we can get. And then the duty cycle will be varied 10 to 90%. What we're going to try and do is compare duty cycle to motor voltage, because we already know from the previous data that I recorded that the motor speed is very linear with respect to voltage as long as we're above about 3 volts on the motor voltage. So we'll collect some data and then you can analyze the data. So here's the specific setup. So here's our optical encoder unit. I'm going to measure the speed with the scope on that. The motor power supply, I've mounted the power components, the power transistor and the diode directly on the unit. This unit will measure the motor voltage and will also record the speed signal and the PWM signal. Okay, so we'll turn it on and we'll be ready to go. Let me just show you, we have power supply, one power supply for the motor. So this 15 volt supply will be used for the motor. This one will be used for the speed sensor, which is just 5 volts. And then here's the ARB generator. So the ARB generator starts out at 1 kilohertz when you start it up. Duty cycle is adjustable easily between 10 and 90%. It's just a 5 volt signal that then drives the base drive. So we'll start at 1 kilohertz and 50%, and then we'll adjust the frequency and the duty cycle together. You do have to turn the output on this unit. So I'll energize the power supply and I will energize the 50% duty cycle. You can see the motor running now. The voltage is 12.1 volts. Okay, these are the 3 scope screens that we'll see. Right now we're triggered on the green, which is the duty cycle, or the blue is the transistor itself. The green is the PWM signal. And you can see that little variation that occurs. We're pulsed on, but we get that feedback from the back EMF. If I trigger on channel 3, or sorry, channel 1, the speed, for the speed measurement. So yellow is the speed, green is the duty cycle signal from the ARB, and 3 is transistor voltage. So I've added the scope channels here. Channel 1 for the scope, that'll be a digital signal to measure. Channel 2 for the pulse duty cycle, this is yellow, green, and finally blue, which is the voltage across the transistor. So this is related to the motor voltage, right? So if we have voltage across the motor and voltage across the transistor, those must add up to the supply. So this one is kind of an inverted view, because when you see voltage here, that means the motor's off. When the voltage is low, that means the transistor is conducting. Okay, we'll collect some data and then you can analyze that. So here are the basic results. I started at 1 kilohertz and we plotted encoder frequency and motor voltage. And you can see the plot here as I go duty cycle, increased from 10 to 90%. Not very linear. If I go to 5 kilohertz, gets a little more linear, although at the low speed I couldn't run the motor, so the voltage dropped too low. 10 kilohertz, again, I didn't get a value at the lowest percent duty cycle, but pretty linear. 15 kilohertz, very linear, and I got speed from 10 to 90%. 20 kilohertz, fairly linear, starts to flatten out here on the top, and then finally 25 kilohertz, it saturates again at the top. So it depends on the speed that you want your operating range around. So clearly the most linear was 15 kilohertz, and it had the widest range of operation from 10% duty cycle to 90%. So it's going to depend on the particulars of your setup, and don't have much load on this motor either. So that will play another role. All right, so that's the data associated with PWM and motor speed control.